Welcome to ECE 3270, Lecture 10. Today we're going to go over a bit of a practical example on how to implement a state machine in the PLC. So let's start with looking at the plain English description of what our state machine is going to do. So this is going to be a fairly straightforward machine. Each time a button called transition is pressed, we want our state machine to progress to the next state. And when it gets to the final state, there are 4 states, so when it gets to state 4, and the transition button is pressed again, we want it to return to state 1. So we're going to use an integer as our state encoding, and then we're going to have 4 states. For inputs, we're going to have the transition button, and we're going to have no outputs. And the transitions are going to look like this. We're going to transition from state 1 to state 2 on the rising edge of the transition button, 2 to 3 on the rising edge of the transition button, 3 to 4, and then 4 to 1. Okay. So the first thing that we can realize is that we've got a single transition button that's going to cause us to transition between each of the states. And it said that we would need to use the rising edge, which makes sense, right? You don't want someone holding the button down and the states continuing to cycle. So if you're in state 1 and someone presses and holds the button, you should move to state 2. You shouldn't then also move to state 3, 4, and then back to 1. So we will need to do rising edge detection on our transition button, and we will need to know the state that we're in to be able to know what state we're moving to. So that's pretty similar to what we've seen before in lecture. So we'll start by checking the state that we're currently in. We do that using an EQU. So we'll check our state, and we'll see if it's equal to 0. The reason we're going to see, well, not equal to 0, less than or equal to 0. If the state is less than or equal to 0, then that suggests that we are outside of the allowed states. So it said that in our plain English description, it said that we were going to have states 1 through 4. So if we are at state 0 or anything less than 0 or anything greater than 4, then we're in an error state. In which case we need to return to our default state, and in this case our default state will be state 1. So we'll move 1 into state if we wind up in an error. Okay. Let's add another rung, and now if we are in state 1, so we check that using an EQU. So if we're in state 1 and the transition button is pressed, then we need to move to state 2. But we can't just use the transition button. We need to use rising edge detection on our transition button. So let's add a rung where we're going to perform rising edge detection. So we have our button called transition, and we know how to do rising edge detection. We know that we're going to need last, and we're going to latch something to say that a rising edge has occurred. And this is going to be our last. So if transition is true, but it was false last time, then a rising edge has occurred, and we should latch rising edge. But we need to do one other thing. we need to remember or store the state of transition in last. Okay, so now if transition rising edge detected is true, then that means that a rising edge has occurred at transition. So if transition rising edge has occurred, rising edge detected, then we're going to move to state 2. Now, so this is how we're achieving this. Detecting our rising edge, storing that we have seen a rising edge on our transition button in transition rising edge detected, and then if we're in state 1 and we have detected a rising edge on the transition button, we move to state 2. We need to do one other thing. We need to turn off transition rising edge detected, because we have now transitioned and it is no longer necessary to transition again. So this takes care of when we're in state 1, but we need to now take care of the situation where we're in states 2 through 4. So the logic is very similar. If we're in state 2 and a rising edge is detected at our transition button, then we move to state 3 and we turn off our transition rising edge detected. If we're in state 3 and we see a rising edge, we will turn off the rising edge and move to state 4. And if we're in state 4 and we have received a rising edge on our transition button, we will turn it off and move to state 1. So now let's download this logic. Now we will set our PLC back to run mode so that our code is executed on the PLC. And now let's half screen our PLC file and half screen our HMI. Okay, so now that we have our PLC on one side and our HMI on the other side, we can see the effect of our code. So when we first downloaded the code, the value in the state variable defaulted to 0. But since it was less than or equal to 0, we immediately did a default transition into state 1. And since the current value in state is 1, this state is lit up on our HMI. Now, let's press transition. Okay, so I've pressed and held transition, and we can see that we transitioned from state 1 to state 2, but we've not continued to transition because we detected the rising edge of the transition button and used the rising edge to generate the transition rather than directly using the button. So now if I release, we'll be able to transition again. So when I released the button, the memory bit called last went off, and so now if I were to press transition, this would become true, and we would latch rising edge detected, and we would again transition. So we were in state 2, and a rising edge was detected, so we moved to state 3. Now we are currently in state 3, and if I press transition, we will generate a rising edge, and we will move, so we are in state 3, and if I press the transition button, there will be a rising edge detected, and we will move to state 4. And finally, if we press transition one more time, we will move to state 1. So notice we use both the current state and our inputs to know what the next state will be. So we use the current state and the input to know what our next state will be. So this is a simple implementation of a state machine. I'll full screen the logic and we'll talk through it one more time. But even though it is simple, it is representative of how most of the state machines you're going to need to code are going to work. So you may not need to rising edge detect the inputs that go to your transitions, but you in some cases might need to do so. And if you were to need to do a rising edge detection on one of your inputs before associating it with a transition, we would do so in the way that we have seen previously in the class. So I'm processing my inputs in this first rung. Next, I have my default state logic for the state machine. So I need a way to handle if for some reason someone were to type in an odd number, a strange number into the state. So let's say I just said we're going to go to state 100. Well, it's going to default immediately back to state 1 because 100 is outside of the bounds that I've set. I've said if our current state is less than or equal to 0 or greater than 4, then move directly to state 1. So this allows us to have a default state as we should with any state machine. Then once we've coded our default state logic, we have our state transition logic. So to transition to a next state, we have to know the state we're currently in and the state of the input. So given our current state and the input associated with the transition out of that state, we move to the next state. And we do this for every transition. So each of these rungs represents one transition in our state machine. And that's our logic. Now, if you had outputs, the way that we would incorporate those outputs would be in a separate group of rungs at the bottom, and those would be controlled only by the state. So if we wanted to have an output associated with this program, we could do so simply by saying we're going to have an output that's only on when we're in state 3. So this output is associated with state 3. State 3 controls that output. So we're going to check to make sure that our current state is equal to state 3. And if it is, we're going to turn on a bit called state is 3. Create the tag. Now let's go to our HMI and let's give this an action. We'll associate state is 3 with a multi-state indicator. And when the variable is 0, we will say not 3. And when it is 1, we will say is 3. And we'll download our logic. Now notice this is not a transition. We're not changing states. What we're doing is we're controlling an output based on being in a certain state. So currently, our state is not 3. Transition, not 3, is 3. So if we look at our code, we are now in state 3, and so we have turned on our output, which is called state is 3. So this is how you would go about coding a state machine, capturing all the transitions based on the current state and the inputs, and then controlling outputs based on the current state.